Great, thank you very much. Okay, so this is lecture number 2 of the introduction to 3D n equals to 4 gauge theories. And so I'm just going to begin with a quick recap of some of the things that I said last time and some of the basic data that was involved in specifying a gauge theory, or 3D n equals to 4 gauge theory. Okay, so first of all, we had a compact Lie group, G. That was the gauge group. And then the matter content of the theory was specified after making some small assumptions by a unitary representation of the group G. And this is telling us what the matter content is. So point 1 or piece of data 1 is associated to vector multiplets, and data 2 is associated to hypermultiplets. And we also discussed the global symmetries that are involved in these theories. So first of all, there's an R symmetry, which all of the theories have, which is SU2 times SU2. And they're labeled with subscripts H and C that kind of refer to Higgs and Coulomb. And then on top of that, well, the R symmetries are global symmetries that act in a non-trivial way on the supercharges. There are also global symmetries that commute with the supercharges, and they're called flavor symmetries. And that also takes the form of a product, which I call G Higgs times G Coulomb. And they depend on those global symmetries. They depend on the data that defines your theory, on this G in the representation rho. So in particular, G Higgs was in something like the residual symmetries left over acting on all of the hypermultiplet fields once you've removed gauge transformations. And G Coulomb, well, we didn't describe the full G Coulomb, but we described at least an abelian subgroup of it, which is sometimes called the topological symmetry. And that's given by, well, the center of the Langlands dual of the gauge group. Or another way to say that, the way that we actually derived it was the homomorphisms from the first fundamental group of G into U1. Or if you like, the Pontryagin dual of the first fundamental group of G. Okay, so this is an executive summary of last time. This is the data and some of the outcomes that you have for a theory. So in today's lecture, I'd like to extend this and introduce some new ingredients into the story. So in particular, I'm going to talk about basically introducing central charges into the supersymmetry algebra and all of the physics or some of the physics that entails. Okay, so here we go. So last time we talked about the Superpotential algebra. So we had some supercharges that I called Q. And then, of course, there was also momenta and angular momenta that generate translations and rotations of space-time. So now we want to look at central extensions of this algebra. So what this means is that we add some additional generators that commute with everything else, basically. And those additional generators can appear in the anticommutator of the supercharges. And so that takes the following form. So here's what the supersymmetry algebra looks like now. There's the term proportional to the momentum P, which we had before. But then there are several central charges that I label Z. And you see the way the form of the central charges is basically constrained by the symmetries of the problem. And so in particular, it has to be kind of symmetric onto interchanging all of the indices. And so, for example, in the first term here, if you want to get a scalar, well, you have to replace the momentum, which is a vector, by something. So you can do that with the invariant tensor of SU2. Oh, sorry. Yeah, but that's antisymmetric. So the thing that you exchange it with has to be symmetric. So this scalar charge here is symmetric in its indices. And so on and so forth. So there are two scalar central charges that I call Z here. And they're clearly going to be charged under the R symmetries. And then there's also a vector or a one-form central charge. So it's got a vector index here. And that's not associated to flavor symmetries, but it has something to do with domain walls. And you can think about the index, the fact that it's a vector is kind of a vector perpendicular to domain walls. Okay. And so both of these central charges are going to play an important role in what I'm going to say. I'm going to talk about the scalar central charges first, and then at some point the one-form central charge will make an appearance. Okay, maybe I'll just pause here after a few minutes and see if there's any questions. What is a domain wall? Okay. I'll come to that. Okay. But yeah, it's like it's a wall between two different states of your system, and we'll see in exactly what sense that's the case a bit later on in the lecture. Okay, thanks. Okay, let me discuss the central charges first, the scalar central charges. So as I just mentioned, just for things to be compatible with the supersymmetry algebra here, the two indices on the scalar central charges, which they were spinor indices, two-component indices for the SU2 Higgs and the SU2 Coulomb, they have to be symmetric. And so 2 times 2 minus 1 is 3. So this is the adjoint representation of SU2 Higgs, or the adjoint representation of SU2 Coulomb. So they're scalars, and they transform in the adjoint representation of one or other of the R symmetries. So there are very natural candidates for what these could be, or like how to introduce these things, which are given by the generators of flavor symmetries. And that's just because, kind of by definition, flavor symmetry generators are things that commute with everything in your algebra. So what we're going to do is to just go ahead and assume that they're proportional. And that turns out to be the case if you work things out in the gauge theory. So, but the way I'm going to introduce it is just to declare that they're proportional. So in particular, the scalar central charge that is a triplet under SU2 Higgs is going to be proportional to the generator of the Coulomb branch symmetry. And the central charge that's a triplet under SU2 Coulomb R symmetry is going to be proportional to the generator of the Higgs branch flavor symmetry. And then the coefficients, the constants of proportionality that relate them, these are what we call Fi parameters and mass parameters. And so those kind of describe historically how they arose and how they appear in the Lagrangian of the theory. So in particular, let's look at each of them and understand where they're valued. So let's first discuss the Fi parameters, which is the first term, the zetas. So first of all, they're valued in the Lie algebra of the Coulomb branch flavor symmetry. That's because they have to be paired with the generator. On the other hand, to get the indices to match, they have to transform in the adjoint representation of SU2 Higgs. And the mass parameter is exactly the opposite of that. So they're valued in the Cartan of the Higgs branch symmetry, and they transform in the adjoint of that should be SU2 Coulomb. So they're kind of a mix of the two. They're charged under the Higgs R symmetry and the Coulomb flavor, or vice versa. And this is the way it comes out in the gauge theory. Okay. So yeah, let me just mention that these here I kind of introduced them abstractly as a central extension of the supersymmetry algebra. But of course, you can get them by adding explicit terms to your Lagrangian that describes the theory. And one nice way to do that is to think about coupling, because we already know how to introduce vector multiplets. You can think about them as coupling to background vector multiplets, non-dynamical vector multiplets for the flavor symmetries, and then turning on expectation values for the scalars in those multiplets. So in particular, the mass parameters, you may recall last time that they have the same index structure as the scalars in the vector multiplet. And indeed, you get them by adding in a non-dynamical vector multiplet for the Higgs branch flavor symmetry, and then turning on expectation value. And you can do the same thing for the Fi parameters, except you need to use a twisted vector multiplet, which is, well, it's basically like a vector multiplet, but you exchange the role of SU2 Higgs and SU2 Coulomb. Okay. So the theme of this talk is really to understand how certain quantities vary, or as you vary these parameters, these masses and these Fi parameters. And many interesting observables, many interesting calculations, both in physics and in mathematics, even going up to fancy things like categories of line operators and two categories of boundary conditions and things like that. They all vary in an interesting way, or maybe even jump in an interesting way as you vary these mass parameters and these Fi parameters. And we're going to try to see a piece of that structure today by studying the vacua of the theory. Okay. So I'm not going to try to do that in general. You see, there's all these indices going about. There's three masses and there's three Fi's. So I'm going to look at a particular slice of the problem, basically. So I'm going to simplify it. So what I'm going to do is just to focus on sometimes what's called the real masses and the real Fi parameters. So what does that mean concretely? It means that I set the components 1, 1 to 0. And I keep the other component, the 1, 2 component, to be non-zero. And I just define that to be zeta and m, just for convenience. So basically, if you think about these as three-dimensional vectors, I'm picking a vector, and I'm kind of aligning my system with that vector. Okay, so this if I turn on non-vanishing expectation values, just because these things are charged under the R symmetry, then they're going to break the R symmetry, and they'll break it down to a maximal torus. So again, this is like picking a vector in 3 dimensions. If you pick a vector, you'll break SO3 down to SO2 that rotates the vector. That's the 2U1 factors here. So first of all, they break the R symmetry down to a maximal torus. And they also will break the flavor symmetry. And if they're generic enough, then they'll break the flavor symmetry all the way down to a maximal torus that I'll call TH times TC. Okay. So basically, turning on generic values of these parameters is going to break the R symmetries and the flavor symmetries down to maximal tori. So abelian subgroups. Okay. So I'm going to focus basically just on these pairs of parameters. And so just to give a bit of notation, since I broke the R symmetry, then it's useful to kind of decompose the fields that I've been using under that subgroup that I've broken to. So in particular, that's fairly straightforward to do. If we look at the vector multiplet scalars, there are 3 of them, and we're just going to decompose them here into a real and a complex piece. The real piece I call sigma, and the complex part I call phi. And in components, they're like this. That second one should be 1, 1 dot, 1 dot, 1 dot, sorry about And then the hypermultiplet scalars, they just decompose into a pair of complex scalars, x and y, which are the same ones that I discussed in yesterday's lecture. So the charges of all these things are summarized in this table. So sigma and phi, well, they both transform in the adjoint representation of G. They're in the vector multiplet. They're not charged under U1 Higgs R symmetry. They used to transform as a triplet of SU2 Coulomb. So now the real bit, that's like the 3-direction, that's uncharged, and the complex one phi has charge 1. X and Y, they transform in this representation R and its conjugate. They used to transform as an SU2 Higgs doublet, but now, well, X and Y bar used to transform as an SU2 Higgs doublet. So now they both have charge half under U1 Higgs, and they're not charged under U1 Coulomb. Okay, so I'm going to be working with these 4 fields throughout: sigma, phi, X, and Y. These are all of the scalar fields in the theory. Okay, maybe here's a good point to stop and see if there are any questions in the chat. Yep, okay, there was a typo, yes, good. Okay, so what I'm going to talk about in today's lecture is to try and understand what the vacua are, or the supersymmetric vacua of the system. So these are the configurations of the fields, classically, that are kind of the vacuum states of the system. They're configurations that are annihilated by all of the supercharges. And they're also configurations that minimize the potential energy of your system. So they're the vacua of the system in flat space. And we'd like to understand what the vacua are. They could be discrete. They could be a moduli space. They could be an extended parameter space of vacua. And so we'd like to understand what type of supersymmetric vacua we have, in particular, and how that depends on the mass and Fi parameters, and how things jump and shift and move around as I vary those parameters. Okay, so here's an important point that I'm not going to talk about at all today, that you should bear in mind, which is that I'm going to talk about the vacua classically. So I'm basically going to think about them as configurations that minimize the classical potential energy of the system. Now, in general, there might be quantum corrections to that. In particular, there can be perturbative one loop and also non-perturbative corrections. They're not going to play a role in my talk today. One can show that they're not there for all of the configurations that I'm going to look at, but they will be there in general. And I'll talk a bit more about that next time. Whether you get them or not depends on the values of the mass and Fi parameters. But for today, I'm just going to think about them as classical vacua. Okay. Good. So you can get the classical vacua by basically minimizing the potential of the theory, like you ordinarily would. And you get a big mess of equations that look like this. I'm going to kind of explain the pieces, and then I'm going to explain a much more elegant way to say what they are, which is much more useful. So the first line here is a real. So I've split it into 2 columns. The equations on the left are real equations. The equations on the right are complex ones. So the top line involves these things called moment maps, and they're functions of x and y. To say formally, like the real moment map is a map from the T star of R, which was the representation, into the dual of the Lie algebra of the gauge group. And the same is true for the complex moment map, except that it's complex valued. Then in the next 2 lines, well, here you've basically got an equation that says if you act with a gauge or gauge plus flavor transformation that's generated by the real or complex scalars, and you act with that on the hypermultiplets, then that has to vanish. And then there are equations that tell you that all of the scalars in the vector multiplet commute among themselves. So we're interested in trying to solve these fairly complex set of equations. Okay, so before I give a bit more, I explain a better way to write these, let me just explain what these moment maps are, because I didn't say very much about those. But it's nothing fancy. One can write down the formula explicitly. So here's the way to think about it. The coordinates x, y, we thought about as kind of coordinates on, they're parameterizing the kind of underlying vector space of our representation. So R plus R star. So this space comes equipped with two natural objects. In the way that I'm presenting it here, they come as a Kähler and a holomorphic symplectic form. So the Kähler form looks like this, and the holomorphic symplectic form looks like this. And both of them utilize the kind of natural pairing on the vector space in its dual, which is kind of implicit in the formulae. And these functions are just this vector space comes with a G action. That's precisely what it means for it to be a representation. And the real and the complex moment map are just the moment maps for that action that are associated, that you would build using the Kähler form and the holomorphic symplectic form here. So if all of that looks very strange, there's just a very concrete formula for it that's written on the bottom line here, which basically shows you that it's kind of a quadratic function of the fields x and y in a way that depends on the representation. So it's something very explicit that you can write down. Okay. So these equations are a bit of a mess, but there's a nice way to think about them, which is useful for giving a more mathematical interpretation of what's going on, and will be important for what I want to say in just a moment. So the way that it's useful to think about these equations, these vacuum equations, is that you want to think about them as the critical points of some function or some set of functions. And just like before, we had the equations, I had the two columns here. There was the real equations on the left, the complex equations on the right. We're going to need two functions that I'll call superpotentials. So there's superpotential H and a real superpotential H and a real superpotential W. And what you can do is, it's very easy to just look at the critical points of these functions. They're functions of all of these four fields, sigma, phi, x, and y. And if you look at the critical points, you'll reproduce exactly these vacuum equations here. So the form they take is fairly nice. If you remember, the moment map was valued in, moment maps are valued in the dual of the Lie algebra. The vector multiplet scalars are valued in the Lie algebra, and so it's natural to pair them together. And that's what's happening here. So in particular, for the real moment map, you're taking kind of you're pairing the real scalar in the vector multiplet with the real moment map for the G action. And then there's also a contribution from the real mass, which involves the real moment map, not for the gauge group action, but for the action of the flavor symmetry G Higgs. And the way you build that is in exactly the same way. Okay. For those of you that know supersymmetry, then W is nothing but the 3D n equals to 2 superpotentials. So if you were to take your 3D n equals to 4 theory and just view it as a 3D n equals to 2 theory, then W would be the ordinary superpotential that would appear in that theory. H is something else. Okay, so there's these nice real and there's these nice real and complex functions whose critical points will give me the vacua. And we're interested in exploring what they are. And so another way to phrase what we're interested in doing is, what are the critical points of these functions, and how do they vary as I vary the mass parameters m and the Fi parameters zeta? That's the problem we're interested in. Okay, let me give an example just to make it a bit more concrete. So last time I had this example of supersymmetric QED with W hypermultiplets of unit charge. And so this corresponded to taking the gauge group to be U1 and the unitary representation to be basically, well, you take the complex vector space of dimension n and you have U1 act in a diagonal way on it. So with weight 1 on each of the factors. So what fields do I have? Well, just to recap, because the gauge group is U1, the adjoint representation is trivial, and the vector multiplet fields are therefore neutral. They have weight 0. And then there are some hypermultiplet fields x and y. There are W of them. The index j goes from 1 to W. And all of them have charge +1 and -1 under the U1 gauge symmetry. We discussed the flavor symmetries last time. The Coulomb branch symmetry was the topological symmetry. And this is just given by U1. Actually, if I need to specialize to W being 3 or more for that to be true. In the case of n equals to 2 is a slight enhancement. And G Higgs, the Higgs branch flavor symmetry is given by PSUW. So this is basically the transformations of the symmetries of the hypermultiplets once I've removed the U1 factor. Okay, so what parameters can I introduce? Well, the Coulomb branch symmetry is U1. That has rank 1. So I've got one Fi parameter, one real Fi parameter. The Higgs branch symmetry is P of SUW. That has rank W. And so there are W masses. Sorry, that has rank W -1. So there are kind of W -1 masses. It's convenient to parameterize them in the following way. So we have W masses, one mass for each of the hypermultiplets, and then we impose a constraint that the sum of those masses is 0. So in total, there's W -1.
And there was a question in the chat in the previous slide. Antoine asks, how does W, the superpotential, transform under the R symmetry?
Yeah, thanks a lot. The superpotential W is going to have, it's going to transform under U1 Coulomb with weight 1, because the complex scalar phi has U1 Coulomb charge 1. And likewise, it was proportional to x dot y, roughly. So it's also going to transform with U1 Higgs charge 1. So normally, if you think about it from n equals to 2 point of view, we often say the superpotential has R charge 2. That's just my choice of normalization. Okay. So the answer to the question is that you can read off the R charges of the superpotentials from this table here. Okay. Does that answer the question?
There was one other question that was just posted just a second ago. Aswin asks, is it possible to think of the pair HW from SQED n equals 4 point of view?
Sorry, from a... I missed the end of the question. Sorry, could you repeat?
Is it possible to think of the pair HW from a 3D n equals 4 point of view?
It seems difficult to do so. I don't think you can write them in a way that's SU2 Higgs times SU2 Coulomb covariant. That might be another way to say the question, to answer the question. So I don't think so, no. Okay, good. So let's continue with this example. So for super QED, there was one Fi parameter and a bunch of masses. So the two superpotentials look like the following. This is just writing out the definitions. And of course, you can see here, if you take the critical points of these functions, you'll reproduce the equations for the classical vacua, which take this form. So here, well, let me just say here you can see the real and the complex moment maps in action. It's a sum over x times y with the charge, which was 1. And here there's a minus sign that comes in because the x's have charge 1 and the y's have charge -1. And they're weighted by the charge. And likewise here, in the second line, you see x comes with sigma because it has charge +1, and y comes with minus sigma because it has charge -1. Okay. All right, so I'm going to make an important assumption, which is fairly constraining. And the motivation for doing this is that, well, this assumption is going to give us a very nice set of theories. And this class of theories are the ones that are kind of most frequently studied in connection with representation theory. Or at least the connection with representation theory is the simplest to describe. So here are the assumptions. The first is that if I turn off these mass parameters, the mass and the Fi's, the theory flows to an interacting superconformal fixed point. That's not going to be too important for what I want to say today. The really important assumption is the second one, which is that when I turn on generic values of these masses and Fi's and make them totally as generic as possible, then there are only going to be kind of isolated, discrete solutions to these equations. Or if you like, these functions h and w will only have isolated critical points. There are no moduli spaces of vacua. And moreover, in each of those vacua, the gauge symmetry G is completely broken. So there aren't going to be any discrete unbroken subgroups or anything like that. So these vacua are all kind of isolated, massive vacua. All of the fluctuations are massive. And so I'll kind of label them by V and an index alpha. So the alpha will be a discrete index. And so let me just say, this is a constraint on the data, G and R. And so it's a constraint on the gauge group and the matter representation. Intuitively, the representation needs to be big enough in some sense that I'm not going to try to describe precisely. And yeah, it's this class of theories that are most simple to make a connection with representation theory. Okay, let's give an example. Let's just check. So here's supersymmetric QED. This satisfies these assumptions when W is greater than 1. And it has, for generic values of the masses and Fi's, it has a finite number of isolated discrete vacua. There are W of them, where W is the number of hypermultiplets. And here, generic means that that you only get a finite number of vacua provided both the Fi parameter is non-zero and all of the masses are distinct. So this is what it means to be generic in this case. And if those two conditions are obeyed, then it's an exercise to check that the only solutions of the vacuum equations, the only critical points of those functions, are given by the following solutions. So if you just look at the case when the Fi parameter is positive, then sigma, the real scalar, is fixed to be equal to one of the real masses. Phi is 0, the y's are all 0, and the x's are fixed in terms of the Fi parameter. And then if zeta is less than 0, then the solutions look basically the same, but x and y are kind of interchanged. Okay. Let me just give another example. So last time we discussed quiver gauge theories, and I introduced this A-type linear quiver gauge theories. And so I just wanted to, because it has a nice bit of representation theory, I just wanted to review that and tell you which classes of these theories satisfy this assumption that I just said. So we have this linear quiver. The gauge group was a product of unitary groups, one for each of the circular nodes. And then there was some number of fundamental hypermultiplets, W1, W2, up to WL, attached to each of the nodes. And then there was some bifundamental hypermultiplets between the gauge groups. So this data that specifies a theory, these numbers, the V's, giving the ranks of the gauge groups, and the W's giving the numbers of hypermultiplets, that data can be encoded in a really nice way in terms of a pair of weights. And they're weights of the Lie algebra whose Dynkin diagram looks like this. So in this case, because the quiver has length L, that's the Lie algebra SL L plus 1. So let me denote the fundamental weights and the simple roots. These are things that are dual by omega and E. Then you can encode the matter representation, the W's. You can encode that in a dominant weight of SLL plus 1 in this way. And then you can encode the data of the gauge group, these V's, in another weight of SLL plus 1 by kind of subtracting a simple root for each rank of the gauge groups here. And so this is, if you like, because I'm starting with the highest weight and I'm subtracting roots, this is a weight in the irreducible representation whose highest weight is lambda. And there's a nice way to say which theories satisfy these assumptions, and they're the theories where mu is also a dominant weight. This is just a nice piece of representation theory that's coming in. Okay, that's all I'm going to say about that, actually. All right. Are there any more questions at the moment, or are we good to keep going? Okay. Okay. So in the last part, in the remainder of the talk, what I'd like to do is to try to address precisely what it means for the mass and Fi parameters to be generic. I mean, we've already seen in this example here in SuperQED that you need to excise kind of codimension 1 loci in the space of masses and Fi's in order to have these discrete vacua. And that's what I'd like to try to formalize in the last part of the talk. So in particular, we have a parameter space of masses and Fi's. And that's just given, that's a vector space. It's given by the product of the Cartan subalgebras of the Higgs and the Coulomb flavor symmetry. And so what we'd like to demand, this is our assumption, is that there are only isolated vacua basically almost everywhere in this space, except on perhaps some codimension 1 loci in that space where bad things happen and a moduli space opens up. And we'd like to determine exactly where these loci are. And so there are a number of things you might try to do. One is just to try to stare at the equations and figure out exactly where these loci are. That's something you can do. But I'm going to try to take a slightly more physical or intuitive approach and think about it in terms of domain walls that tunnel between pairs of vacua. And the basic idea is that when a domain wall has zero tension, that indicates that a moduli space is opening up that connects two vacua. Okay, so let me try to describe that. So I'd like to think about a configuration where you have, say, one massive vacuum at plus infinity, call it beta, and one massive vacuum at minus infinity, call it alpha. And then for that configuration to be consistent, there ought to be a domain wall. So this is just a wall that kind of separates two phases of the theory. On the right, we have a massive vacuum beta, and on the left, we have a massive vacuum alpha. Now, we don't just want to consider any domain walls, we want to consider some that preserve some supersymmetry. And so here, what we can do is we can preserve a 2D, so the domain wall itself is two-dimensional. That's the x1, x2 plane. And we can preserve a 2,2 supersymmetry. And when you do that, 2,2 supersymmetry has a vector R symmetry and an axial one. The vector R symmetry becomes U1 Higgs, and the axial R symmetry is U1 Coulomb. And so here's where this superpotential H is really important, because domain walls, if they're to preserve 2,2 supersymmetry, one can look at the BPS equations for those supersymmetries. And what you find is that domain walls have to be solutions of the gradient flow equations for the real superpotential H. So I'm not going to write out exactly what they are, because it's really not going to matter for what I want to say. But they look schematically like this. So there's some space that's parameterized by the real scalar sigma together with x and y. And there's a function h on it, the real superpotential. And we're studying gradient flow. Gradient flows between critical points. And we think of those as domain walls. So a domain wall is basically a gradient flow for h that interpolates between critical points alpha, say, at minus infinity and beta at plus infinity. Okay. And the idea is going to be that if the tension of such a domain wall goes to zero, then that indicates that you can pass from one vacuum to the other without costing yourself any energy. And that indicates that a moduli space is opening up. So let's talk about the tension of such a domain wall then. So the tension is basically just the energy per unit area in the plane of the domain wall. And one can check that, and this is a very common thing in supersymmetric theories, that the tension of this domain wall is basically proportional to the difference between the value of the superpotential H at the two vacua. So this is a natural quantity when you're studying gradient flow. It's the difference between the values of the function at the two vacua. And this is the tension of a domain wall, of a BPS domain wall. It's useful to point out, because you may have noticed that so far I haven't discussed the vector central charge at all. I only discussed the scalar ones. This is basically the vector central charge. In the presence of such a domain wall, you'll get a non-vanishing vector central charge of this form. The component 3 means that it's a vector in the 3 direction. That's because we're looking at domain walls perpendicular to the 3 direction. So this is where the vector central charge comes in. It controls the tension of domain walls between vacua. Let me mention another thing, which I think is underappreciated, but is very useful, which is that the value of this real superpotential H in a vacuum has a really nice physical interpretation. It's a Chern-Simons term, actually. So in the SUSY gauge theory, it takes the following form. It's basically a bilinear function of the masses and the Fi parameters. So I apologize, T here should be zeta. It's a bilinear function of the Fi and the mass parameter. Or if you like, it's a bilinear pairing. That's a formal way to write it. Moreover, it's not just a real bilinear pairing. It lifts to a kind of discrete thing. It lifts to a bilinear pairing on the co-character lattices. So these are lattices that sit inside of the Lie algebra. And it lifts to a pairing on those lattices, an integer pairing on those lattices, on those lattices. And this is nothing but the effective. It's just an effective mixed Chern-Simons term between the two flavor symmetries in the vacuum. So normally, in an n equals to 4 theory, you can have a mixed Chern-Simons term between a vector multiplet and a twisted vector multiplet, and this is what's happening here. But it's a mixed Chern-Simons term that you would get in your massive vacuum by integrating out all of the fields and computing the Chern-Simons term that induces. So this is nothing but an effective Chern-Simons term. Okay. So that's another way to kind of give an interpretation to the function H.
So there was a question in the chat
okay.
just a moment ago. The question was, does W not enter in the domain wall BPS equation or vector central charge? A question from the previous slide.
Does W?
Mm-hmm.
Yeah, great question. Thank you. I skipped over that. No, it doesn't. You should just supplement this with dW as 0. So there's no kind of gradient flow for W. You just impose that you need to sit at a critical point of it. This is just the BPS equations for 2,2 supersymmetry. They're basically gradient flow for H and sit at the critical points for W. Yeah. Okay. Good. So let's then try to talk about the condition of what it means for the masses and Fi's to be generic. So the key argument, the idea is that if you have two massive vacua, you can have domain walls that kind of tunnel between them. And if the tension of such a domain wall vanishes, then that means you can go from one vacuum to the other without kind of costing any energy. And so that indicates that those vacua are not actually isolated anymore. There ought to be a moduli space or a parameter space that connects the two. And these are the walls, these are the kind of loci where not bad things, but interesting things happen. So the picture looks something like this. So if I think of this parameter space of masses and Fi's, which is the product of the cartans of the flavor symmetries, at a kind of very generic point, then you're going to have just discrete isolated points for your vacua. So I represent this by 2 points. But then if I start to move around, I start to vary slowly the mass and Fi's until I sit on one of these walls or one of these loci where the tension vanishes. So here, this is the locus, W alpha beta is the locus where a domain wall between the vacuum alpha and the vacuum beta becomes tensionless. At that point, what I can expect to see is a moduli space opening up, a non-trivial moduli space that connects those two vacua. So here I've kind of drawn it as a two-sphere. It's not quite true, but it's but the point is that there's a moduli space opening up that connects the two. And then again, I might continue this picture. There may be many lots of walls, and I get a very nice intricate structure where I start to, I might go on one wall and then another one, and then the moduli space gets bigger and bigger and bigger until I get right to the origin, but the masses are just 0, and I have a very big moduli space indeed. Okay, so this is the kind of broad picture. So I'd like to make an important point, which is essentially that the equations that define these walls, these walls here, are linear, or bilinear in the masses and FIs, precisely because these kappas were bilinear. So what that means is that if I say fix the FI parameter and look at the image of this locus in the space of masses, it will define a linear hyperplane through the origin. So I can project these walls down onto the spaces of masses and FIs, and they'll give me kind of linear hyperplanes. And you know, and these hyperplanes, they kind of cut the spaces up into chambers. So if I look at the connected components of the complement of these hyperplanes, if I just excise them, then they'll kind of split into chambers, where, like, you know, the vacuum structure is kind of constant, and then as I cross over a wall, then things might jump. And these hyperplanes, they're all hyperplanes through the origin, and so they form a kind of root system, or if you like, a pair of root systems, one in T Higgs and one in T Coulomb. So for every theory, I kind of get a root system. And this is kind of a first hint of connections to geometric representation theory. These will be the root systems of some interesting algebras that one can build from studying these theories in more detail. So that's hard to imagine without an example. So let me give a very concrete example. So let me consider this example of super QED. So we've already seen that for generic values of the parameters, there are W isolated vacua. We found out what they are. So in this case, a simple exercise is just to compute the value. Well, we worked out precisely what the vacua were. So it's a simple exercise to just plug that back in to the function h to find what the values of the function h is at the vacua. And it's just given by this expression here. You see it's bilinear in the FIs and the masses. And in fact, it's just the FI times the mass of the hypermultiplet that gets a VEV in that vacuum. So if we look at domain walls, they become tensionless on these loci here, W alpha beta, where zeta times the difference between the mass alpha and the mass beta vanishes. And this reproduces, you know, exactly the conditions that we had before. You know, if you just look at the equations that you have for the critical points, you can just check that in order for there to be isolated, you need zeta to be 0 and the masses all to be distinct. And that's the statement that you need to sit yourself away from any of these hyperplanes, away from any of these loci here. Okay. Let me draw a picture. So let's just take an example and project onto the Higgs branch symmetry, the mass parameters. So in this case, the space of mass parameters is a copy of R to the W minus 1. So that gets harder and harder to draw as W gets bigger. So let me focus on the case. I apologize. This is because I switched notation. Let me focus on the case when W is equal to 3. So if there are 3 hypermultiplets, and then I'm just looking at an arrangement of hyperplanes in R2. And so the picture looks something like this. If I take the difference of the masses and use that to coordinatize the space, Then there are three hyperplanes, W12, W23, and W31, where domain walls between pairs of vacua become tensionless. So, well, this is basically the root system of SU3. And more broadly, if you look at the more general case with W hypermultiplets, the kind of independent hyperplanes that you get after projecting down here are labeled by pairs of vacua where alpha is less than beta. And those hyperplanes you can basically think about as root hyperplanes associated to positive roots of SLW. And so you've got a kind of root system here. And that's no coincidence. As you start to develop these theories and study more interesting and complicated observables, you end up building these algebras, and they're built in such a way that their root system is obtained in this way. So we're starting to see a bit of connections here to geometric representation theory. Okay, so that brings me to the end of my talk. Since I'm almost at the end, maybe I'll just summarize what I'm going to do next time, and then see if there are some more questions. So in today's lecture, I introduced central extensions of the super-Poincare algebra and masses and Fi parameters. And we were trying to study what happens for like the most generic possible masses and Fis, and where there are kind of isolated discrete vacua. Next time, we want to do the opposite. We want to precisely put ourselves on these loci where moduli spaces open up, and to study what those moduli spaces are. And in general, it's a very intricate structure that you get. But there are some kind of distinguished loci that you can go to. And in particular, we'll study particular moduli spaces that open up, called the Higgs branch and the Coulomb branch, that I mentioned right at the beginning, and the kind of mathematical structures that these are the geometric structures that these spaces have. In particular, I also explain how you can kind of reformulate everything we've done so far from the point of view, from geometry, basically, from the geometry and topology of these spaces. So how to recover flavor symmetries from the geometry and topology of these spaces, and how to recover these hyperplane arrangements from those spaces as well. Okay, so let me finish there and see if there are some questions.
Well, thank you very much for an excellent talk. I really enjoyed it. We'll open for questions now. I see there was already one question in the chat from a moment ago.
Okay.
Antoine is asking, can you say anything about the case where the mass matrix is not diagonal, e.g. nilpotent?
Yeah, I don't think I have anything intelligent to say about that. No. It's in it, yeah. I mean, I'm aware that one can do such things, and it's interesting to do them. Yeah, I don't. I guess I don't have anything useful to say. I don't know if it's connected to the kind of things in representation theory that I was aiming at.
If other people have questions, you're welcome to either raise your hand or post in the chat, and I can unmute you. Does anyone have any questions?
Yeah. So yeah, I was wondering how much of this discussion carries over to, let's say, sigma models.
Yeah, that's a great question. In some sense, that's pretty much what I'm going to talk about next time. So, next time I'm going to basically flow to a sigma model onto the Higgs branch or the Coulomb branch, and then try to explain how to reproduce exactly all of the structures that I've talked about today. So in particular, what the flavor symmetries are, what the parameters are that you can turn on, and these kind of nice hyperplane arrangements that you get in the space of those parameters. So yes, the answer is yeah, you can think about them from that point of view.
So as a follow-up, say I have like a sigma model on some hyperkähler target space. How general is my allowed choice for the pair HW? Is that something I can just choose, or is that so in the gauge theory it's kind of given to you by the matter and so on, but in the sigma model do I actually have a choice of what H and W to choose?
No, I mean you don't directly have H and W, but what you will have is so if you remember in H, a piece of that was the moment map for the flavor symmetry action.
Yeah.
And that's the piece that you'll have in a sigma model. So it's not a dynamical thing, because you're not trying to pass to the critical points of it in the sigma model. In some sense, you've already done that. You know, basically it will be replaced by the moment map that in a sigma model, one of the flavor symmetries. So say that I pass to a sigma model onto the Higgs branch, for example, then the GH symmetry will act by isometries on the Higgs branch, and there'll be a moment map for that action. And that moment map will be the analog of H. In fact, there'll be a real and a complex moment map, which will be the analog of H and W.
Okay. Thanks.
So in principle, they're fixed. You know, there's no additional choice. They're fixed by, you know, what isometries does the space have.
So just to give my question a little context, maybe you already answered, but so I'm just thinking that if I have some Kähler sigma model, then, you know, the superpotential I choose is a choice, right? I can just deform the sigma model with the W by adding some. So there's no analogous construction in 3D n equals 4 with hyperkähler target spaces.
No, I think if you want it to preserve n equals to 4, there's no further choice to be made.
Okay, thank you. Yeah.
Okay, well, I'm happy to chat off the record.
Yeah.
If you like.
Okay, well, great. Yeah. Thank you so much, Mathew. We can probably